I want you to consider the following two scenarios. So scenario one has a cliff and a box sitting at the top of the cliff, and scenario two has an identical box sitting at the bottom of the cliff. So since the two boxes are stationary, neither have any kinetic energy. However, with just a little push, the box at the top of the cliff can rapidly acquire a great deal of kinetic energy. By contrast, it would take a lot of effort from a lot of external forces to give box 2, that's at the bottom of the cliff, the same amount of kinetic energy. You could say that box 1 at the top of the cliff has more potential to acquire kinetic energy than box 2. Now, physicists have developed the concept of potential energy to account for this difference between the two boxes. And when we're talking about the box being in the gravitational field, it's naturally called gravitational potential energy. And we say that it's an energy stored in the gravitational field or due to the gravitational field. So what variables does gravitational potential energy depend on? Well, here's our equation for gravitational potential energy, and note that we can write it either as Eg, or often it's just referred to as EP if that's the only potential energy term that we're looking at. So you can see here that the potential energy due to gravity is equal to mgh. Obviously, the gravitational potential energy depends on the mass of the object, and often we would give that in kilograms. It also depends on the acceleration due to gravity in meters per second squared. Now, this makes sense if you think about for something which is being pulled down by the gravity on Earth, it would gain more kinetic energy than, say, you're on the moon, where the force due to gravity is smaller, your acceleration due to gravity is smaller. It also depends on the height you're at above some arbitrary reference point, and I'll go into that a little bit more detail later, but we can say that height is h and we measure it in meters. I also want to point out that, of course, the gravitational potential energy equation here contains that mass term, and that also makes intuitive sense. So if you drop a heavy object and a light object from the same height, the heavy object will make more of an impact when it hits the ground, and that's an indication that it's gained more kinetic energy when it's fallen. Now, the units of potential energy are also in joules, and you can look at this and work this out yourself. If you look at the units of those variables there, mass, acceleration due to gravity, and height, you can see that the equivalent unit of joules, again, is kilograms meters squared per second squared, which is consistent with the kinetic energy that we looked at before. We're going to now talk about elastic potential energy. And elastic potential energy, sometimes I'm going to refer to it as spring potential energy, is the energy stored due to compressing or stretching a spring or some other elastic type of material. Now, it turns out that elastic potential energy is actually just due to electromagnetic interactions between the particles in the spring itself, but we use the term elastic potential energy or spring potential energy for springs or elastic bands or anything that stretches and compresses but then bounces back to its original state. So it's a kind of a general term we use for those macroscopic phenomena. So elastic potential energy or spring potential energy, and this is for the case of a spring or something that follows Hooke's law. So as something where the force is proportional to the extension of that spring, takes the form of this equation here. So that's our spring equation. Just to look at some of these variables in here, K is the spring constant, and that comes from that force versus extension graph. It's the slope of a force versus extension graph. And K has the units of newtons per meter, as you can see from that F equals Kx. You rearrange that to find the units there. And X is just the extension from the equilibrium position. We measure it in meters. Now, the units of spring potential energy or elastic potential energy are in joules, or you can see they're Newton meters. So if you play around with the units on the right-hand side of the equation there, you have newtons per meter and then meters squared there, you'll find that those units of joules are equivalent to Newton meters. And you can also show for yourself that these units of Newton meters are also equivalent to what we had before with kilograms meters squared per second squared. And it's quite a nice exercise to go through.